Hey everyone, this is Mr. K. Welcome back to Everything is Relative. And today we're going to be doing another topical past paper video where we're going to be looking at past paper questions from the topic of capacitance for Cambridge A-level physics from the Papa Cambridge website. Now, as always, I'll leave a link to the website and to these questions in the description below, and you should be using these questions as one of the resources for preparing for your final Cambridge A-level physics exam. And today we're going to be looking at questions on capacitance that deal with the initial link with capacitance and electric fields. And the next video I will do the link between capacitance and the structure of the capacitors and how energy is stored on the capacitors and so on. And so we're going to be doing questions 196 to 202 as they're numbered on the Papa Cambridge website. And the question numbers might be a bit fuzzy, so I'm just going to write them down. The first question we're going to deal with is 196. And the subject code for A-level physics is 9702. This first question comes from the March 2021 exam. It's question paper 4, variant 2. And this is question 6 from that exam paper. And the first question says to state a similarity between the gravitational field lines around a point mass and the electric field lines around a point charge. Now what we know is that gravitational field lines always point inward because gravity is always attractive, but electric field lines can point inward or outward. So that's not a similarity. But there is one thing about a point mass and a point charge that will be the same. The field lines will both be radial. And so straight away I can just state that. I only have to state one similarity, and I can make that similarity that both of them have radial field lines. So both a stationary mass and a stationary charge will both have point mass and point charge, that is, will both have radial field lines. The gravitational field lines will point inwards, and the electric field lines may point in or out depending on whether the charge is positive or negative, but they'll both be radial in shape at least. We're then told that the variation with radius r of the electric field strength, E, due to an isolated charged sphere in a vacuum is shown in the figure. So I'm given a graph of electric field strength against distance for an isolated charged sphere in a vacuum. And I want to use data from the figure to state the radius of the sphere. So what I see is a graph that's 0 for the first 2.1 centimeters. It then jumps to a maximum value of 1.3 times 10 to the 5 volts per meter. Don't forget the 10 to the power 5. And then as you move away from 2.1, there's a very significant decrease of the electric field strength. So how do I look at this graph and tell what the electric field, or rather what the radius of the sphere is? Well, what do I know? Inside the sphere being a conductor, inside a conductor, the electric field strength is 0. So if I'm measuring my distance from the center of the conductor to the surface, the electric field strength will be 0 inside from the center of the sphere to the surface. The distance over which the electric field strength is 0 is my radius. And so I simply need to read that distance off for which the electric field strength is 0. And I can see that the point I've drawn the x at is 2.1 centimeters. So I can simply read that off from the graph. Inside a conductor, the electric field strength is 0. And so that's how I can tell the radius of the sphere. I'm then told to calculate the charge on the sphere. Okay, so now I'm not actually given any information besides the radius. Well, I'm not explicitly given the information, but I can take the information, I can infer what I need to from the graph. So the first thing I need to do is find an equation that's going to relate electric field strength, distance, and charge. Thankfully, I have that. The electric field strength at a certain point is 1 over 4 pi epsilon naught times the magnitude of charge that will be stored in the sphere divided by the distance to the point squared, r squared. So what I need to do now is I need to find a value for r and a value for e. Well, luckily for me, I have a whole graph of values to choose from, so I'm just going to take a random point in the graph. I'm going to take a point where r is 0.021. So I'm going to use the maximum value of the electric field strength, the one we just spoke about. So when we are at 2.1 centimeters or 0.021 meters, the electric field strength, as we've seen, is 1.3 times 10 to the power 5. Don't forget powers of 10 when you're reading off values from the graph. 1.3 times 10 to the power 5 volts per meter. Now, if I put those numbers into this equation, I can solve for the charge. So what I get is Q is 4 pi epsilon naught E, the electric field strength, times R squared. Now I have all of these values and I can put them in to solve for the charge. And this is 4 pi epsilon naught is 8.85 times 10 to the minus 12 farads per meter. You can find this value in your data sheet. That's the permittivity of free space. The electric field strength, again, doesn't matter which value you choose, but you have to make sure that the value of R corresponds with the correct value for E. And that's 1.3 times 10 to the 5, and R is 0.021 squared. And what I get is a charge of 6.38 times 10 to the minus 9 coulombs. And to two significant figures, this is 6.4 times 10 to the minus 9 coulombs, or 6.4 nanocoulombs. The answer did ask us to write the value in terms of coulombs. Okay, so what I need to do there is write an equation that has the electric field strength, has distance, and has charge in it, rearrange and solve for Q, but then I need to go and find values for E and R. So if you have a graph, it's basically that you aren't given explicit values, but you can take values from the graph itself. We are then told that using the formula for the electric potential due to an isolated point charge, we are asked to determine the capacitance of the sphere. So there's a question on capacitance, albeit quite briefly. Now, what is capacitance? By definition, capacitance is charge per unit potential. So it's the charge Q, and you can see that this question links to the previous one, divided by the potential. Now, I'm going to consider the surface of the sphere, and I'm going to write the potential as 1 over 4 pi epsilon naught Q over R. This is the equation for electric potential. Again, this is something you can find on your data sheet, on your formula sheet rather. If you look closely, you see that the Q's disappear, and all I'm left with is a nice equation for capacitance, which is 4 pi epsilon naught times R. So if I want the capacitance of the sphere, I must evaluate this expression where R is the radius of the sphere, because the capacitance is on the surface of the sphere. And if I put my values in, I get this to be 4 pi times 8.85 times 10 to the minus 12. And the radius of the sphere we determined to be 2.1 centimeters or 0.021 meters. And this will give me a capacitance of 2.34 times 10 to the minus 12 farads. To two significant figures, again, this will be 2.3 times 10 to the minus 12 farads. A very small value for capacitance, and so too a very small value of charge, but you'd expect this. Anything, just remember as sort of a rule of thumb, that anything that can be carried out in a lab, any experiment that looks like a lab experiment like this one, there generally will be low values of charge and low values of capacitance. We're talking about picofarads, nanofarads, microfarads, and so on. Now, that question was worth 7 marks, and there was a little bit of mathematics involved, but nothing out of our abilities. The next question is 197. And this is from the summer exam of 2021, summer being May, June 2021. This is question paper 4, variant 1, and question 7 from that paper. And the first thing we are asked is to state what is meant by the capacitance of a parallel plate capacitor. So not just a capacitor, but specifically a parallel plate capacitor. What is meant by the capacitance of any capacitor? Well, it is the charge per unit potential. But since we're talking about a parallel plate capacitor, we have to be a bit more specific. It is the charge. Now, the charge on a parallel plate capacitor is the magnitude of charge on one of the plates, because both plates have the same charge but different signs. So I'm going to say it's the charge on one plate of the capacitor, and this question comes up a lot, divided by, now potential is difficult to state potential for a parallel plate capacitor, but we consider the potential to be the potential difference between the plates. So I take the amount of charge stored in one of the plates, which is the charge of the capacitor, divided by the potential difference between the plates, and it gives me the capacitance of the capacitor. So slightly different from our definition of what capacitance is for any conductor. This is specifically for a parallel plate capacitor. And it's a common type of question. We're now shown in question B a capacitor of capacitance C connected into a circuit as shown. When the 2A switch is in position A, the capacitor is charged so that the potential difference across it is V. The switch moves to B and the capacitor fully discharges through the sensitive ammeter. The switch then moves rapidly between A and B, so the capacitor charges and this discharges with frequency F. And we want to show that the average current I in the ammeter is given by the expression I is equal to FCV. Okay, so this expression I've never seen in my life before. But what's happening is the circuit is initially in such a way that it is closed to A, and so the right-hand part of the circuit is completely ignored. Current flows from the power source and charges the capacitor. And after a certain time, the switch flips to B, the capacitor, which is now charged, discharges across the ammeter, and the ammeter reads the current. And the rate at which the flipping happens is the frequency. So the number of times per second that the switch flips between A and B is the frequency F. So the current in the ammeter, I, is going to be the charge that passes through the ammeter divided by the time. Now the charge that flows through the ammeter is the charge that's being stored on the plates of the capacitor. But remember that capacitance is charge per unit potential, which means that charge is capacitance times potential difference in this case. So I can write Q as C times V. Now the time that this happens is the period for the switch to flip between A and B. Remember, 1 over frequency is the period, so I can write this as CV over capital T uppercase T being the period. And then what I get is that the current I, because I remember that 1 over period is frequency and 1 over frequency is period, I get this to be FCV as required. So it may be an expression that I haven't seen before, but it is one that I also can derive using my knowledge of current, my knowledge of capacitance, and then my knowledge of periods and frequencies. So a little bit of mathematics, but not very long. So expect to see questions like these where you need to derive something and then possibly use it, well actually more than likely use it later on in a calculation. Next, we are told that for a potential difference V of 150 volts and a frequency of 60 Hertz, the average current in the ammeter is 4.8 microamperes. And we want to calculate the capacitance in picofarads of the capacitor. So I said that I is FCV, which means that the capacitance C is I over FV. So I'm now confident that I had to do the derivation in the previous question so that I could use it here. Since I'm given the current, the frequency, and the voltage, I can put them all in. So the current is 4.8 times 10 to the minus 6 amperes, 4.8 microamperes, divided by the frequency of 60 Hertz times the potential difference across the plates, 150 volts. And what I get is 5.33 times 10 to the minus 10 farads. But the question specifically says, tell me what the capacitance is in picofarads. So pico is 10 to the minus 12, so I need to write this in as 10 to the minus 12. So it's 533 times 10 to the minus 12 farads, which means my capacitor, two significant figures, is 530 picofarads. Two significant figures because, well, all of my values are actually given in two significant figures here. And so the capacitance is 530 picofarads. Again, small value of capacitance, as usually will be the case. We're then told that a second capacitor having the same capacitance as the capacitor in B is connected into the circuit of figure 7.1 and the two capacitors are connected in series, state and explain the new reading on the ammeter. Okay, so all I'm doing is taking the circuit and adding a second capacitor, which is identical to the first, in series with the first. So C and another C. And I want to know what happens to the reading on the ammeter. I want to know what happens to the current. So let me first have a look at some mathematics and see what I can tell about the new capacitance. Well, 1 over the new capacitance is 1 over C plus 1 over C. Remember, when capacitors are in series, this is how we find the equivalent capacitance. So what I find is the total capacitance, the new equivalent capacitance, is half the original capacitance. When we add capacitors in series, we reduce the equivalent capacitance. And what we also know, so the capacitance is now halved, and C is equal to I over FV. The frequency and voltage is staying the same. I'm not doing anything to the potential difference, nor am I changing the frequency. So what this means is the capacitance is proportional to the current. So if the capacitance halves, so too does the current. So the old current was 4.8 microamperes. The new reading on the ammeter, the new current will be 2.4 microamperes. And so I have to write that down, but I also need to explain why I'm saying this. So I'm going to say what I did mathematically, but kind of say it in words. So the total capacitance is halved, and since F and V are constant, at least constant in this case, the current is proportional to the capacitance, as I showed in the equation that I've written down. So the current is proportional to the capacitance. Capacitance is halved, hence the current is halved. So I'm indirectly saying that the reading on the ammeter is halved. Well, obviously, the current is halved, and whatever you read on the ammeter will be the current, which will also be halved. So capacitance halves, and capacitance is proportional to current, so current is halved. And so you wouldn't actually know that it was a true thing unless you were given the equation that they asked us to derive. So you can see there was a lot of linking back to the first sub-question, which is usually the case. So look for these patterns. Don't try and recreate the wheel when you are trying to answer these questions. Always look back to the information that you're given. So a new novel kind of 9-mark question, which was quite mathematical in nature. The next question is number 198. And this comes from the summer 2021 exam. This is question paper 4, variant 2, and this is question 6 from that paper. We are told that two flat metal plates are held a small distance apart by means of insulating pads as shown in the figure. And the first thing they ask us is, explain how the plates could act as a capacitor. Now we know that the structure of a parallel plate capacitor is very similar, but these are just two random metal plates. So how can we turn these metal plates into a capacitor? Well, the first thing we can do is apply a potential difference between the plates. So if a potential difference is applied between the plates, what happens? The plates begin to store charge, or the plates begin to store energy. And so energy can be stored if I simply apply a potential difference between the plates, and that's exactly that would happen in a capacitor. So if I apply a potential difference between the plates, I'm separating charge, rather I shouldn't say storing charge, I'm separating charge and storing energy, just as energy can be stored in a capacitor. And so in a sense, this is a very large capacitor if I were to do this. The arrangement in 6.1 has capacitance C, and the arrangement is connected into a circuit shown in figure 6.2. So we're given a circuit very similar to that of the previous question. When the two-way switch is moved to position A, the capacitor is charged, so the potential difference across it is V, and then it's moved to position B and discharges across the ammeter. The switch moves repeatedly between A and B, so the capacitor discharges and charges and then discharges with frequency F. And if you think about the similarity in the symmetry with the previous question. You probably could see where this question was going. Show that the average current in the ammeter is given by I is equal to CVF. So like we did before, current is total charge divided by total time. Total charge, this is from the capacitance equation, is C times V. The charge stored on the capacitor is the charge moving through the ammeter. And the time taken is the period for the switch to move between A and B, because it has a frequency f. But what we know is 1 over the period is equal to the frequency. So I can write this as CVF, because frequency is 1 over period. We remember this from multiple topics. So then I get the current is CVF as required. We are then told that for a potential difference V of 180 volts and a frequency of 50 hertz, the average current in the ammeter is 2.5 microamperes, and we want to find the capacitance in picofarads again of the parallel plates. So I can do exactly the same thing. C is I over VF. Take the equation that I'm given, rearrange it, and solve for C. So this is a current of 2.5 times 10 to the minus 6 amperes divided by a voltage V of 180 volts times a frequency of 50 hertz. And I get a capacitance of 2.78 times 10 to the minus 10 farads. But I need to get picofarads, which is 10 to the minus 12. And so I can write this as 278 times 10 to the minus 12 farads, or 280 to two significant figures, 280 picofarads. Again, a very small capacitance. We're then told that a second capacitor is connected into the circuit of figure 6.2, and the two capacitors are connected in parallel. We want to state and explain the change of any in the average current in the ammeter. So instead of in series, I have a second capacitor placed in parallel with the first capacitor, and I want to know if anything happens to the reading on the ammeter. So is the average current in the ammeter going to change? Well, let's go back to our knowledge of capacitors. If I put capacitors in parallel, then the equivalent capacitance is the original capacitance C plus the new one. I'm going to call it C new. But immediately I can see that this value, no pun intended, but this value of C equivalent rather, is greater than the original value of the capacitance, because you put two capacitors in parallel and the equivalent capacitance is greater than any one of those two. So it's greater than the original value C. But the value C was equal to I over VF. V and F remaining constant means that C is directly proportional to the current I. So what this means is if I increase the capacitance, I'm going to increase the current as well. So I need to state what I did in mathematics in words. So I can say that the total capacitance increases. I don't have to explain why. It's understood. It's expected that I understand this. Total capacitance increases in parallel. Then I can say since V, well, you'd say since potential difference in frequency, but using the symbols should be fine. Since V and F are constant, capacitance, like I said before, is proportional to current. So obviously current will increase as well, because capacitance increases and current is proportional to capacitance, so current increases as well. And so when you connect a capacitor in series and connect it in parallel, two different things will happen. And this is an example of how those two things will happen in practice. And so another 8-mark question on capacitance. And we can see we mix it up with theory and mathematics and deriving equations even. And so capacitance can be a significant topic. The next question is question number 200. And so this is question number 200. This is again subject code 9702 for A-level physics from the winter 21 exam. That's October-November 2021. It's question paper 4 variant 2 and question 6 from that paper. And we start off slightly differently. We are asked to define electric potential. So it's going to take your knowledge back to electric fields. Remember, you have to know your electric fields well if you're working through questions on capacitance. My suggestion would be to understand the topic well before moving on to capacitance. What is electric potential? Is the work done specifically per unit charge in moving. I have to be more specific when I talk about electric potential rather than gravitational potential, in moving a positive charge from infinity. And I'm going to stop the definition there because they didn't say define electric potential at a point, but they said define electric potential. It's the work done per unit charge to move a positive charge from infinity to wherever. As I move the charge to different points, then the electric potential will be different points because I require more work to do that. So it's the work done per unit charge in moving a positive charge from infinity. Next, we are told that an isolated conducting sphere in a vacuum has radius r and is initially uncharged. It is then charged by friction so that it carries a final charge q, and this charge can be considered to be acting at the center of the sphere. By considering the electric potential at the surface, show that the capacitance is given by 4 pi epsilon naught r. Aha, we actually came across this earlier, even though we weren't asked to prove it. What is capacitance? Capacitance is defined as charge per unit potential. It's the charge stored on the sphere Q divided by the potential of the sphere at its surface. So it's Q divided by what is the potential of the sphere at its surface, 1 over 4 pi epsilon naught Q divided by r, where r is the radius of the sphere. And if you look carefully, you see that the q's disappear. The 1 over 4 pi epsilon naught r can go to the numerator and become 4 pi epsilon naught r. And so with very little mathematics, we can show that. So remember what the definition for capacitance is. Put in your equation for electric potential, and you'll see that the mathematics works out for itself. So it's something that may creep up at some point. You aren't expected to remember this expression, but you could be asked to derive it. Next, we have a very interesting question. We are told that the dome of an electrostatic generator is a spherical conductor of radius 13 centimeters, and it is initially charged so that the electric potential at the surface is 4.5 kilovolts. A smaller isolated sphere of radius 5.2 centimeters, which is initially uncharged, is brought near to the dome, and sparking causes a current between the two spheres until they reach the same potential. And we want to assume that any charge on a sphere may be considered to act as a point charge at its center. We want to find the charge that is transferred between the two spheres, not the original amount of charge that the large sphere had. So I find this question quite tricky, actually. And to help me understand it, I'm going to draw a diagram. And I'm going to draw the large sphere, again, very poorly, but you can understand that it looks spherical-ish. The large sphere has a radius big R, and the small sphere has a radius little r. So I'm just going to label the radii of each of these spheres. And the big sphere initially has a charge Q and a potential difference V. And so I'm going to say this is the initial scenario. And the small sphere is initially uncharged. So zero potential, zero charge. It's just a neutral. After the sparking occurs, what I have is the new sphere transfers little q of charge to the small sphere. It now has a potential, I'll call it V2. The charge that remains on the big sphere is big Q minus little q, because little q is now gone to V2, and remember, charge must be conserved. And the big sphere now has a potential V1. Now, the reason I do this, and you don't need to do this, is because I like mathematics, and I like to have a picture that I can understand when I'm doing my algebra. So what I know is that big V, the potential in the big sphere initially, is 1 over 4 pi epsilon naught times its charge Q divided by its radius R. That's the potential on the big sphere. That means the charge on the big sphere big Q is 4 pi epsilon naught V times R. Now I could put numbers into this and I could solve this immediately because I know big V and I know R, the radius of the big sphere. But I'm actually going to leave it because I'd rather put the values in a lot later. For the final scenario, so that was the initial picture. For the final picture, what I have is that the potentials become equal. So I have V1 equal to V2. And mathematically, what does this mean? That means 1 over 4 pi epsilon naught times big Q minus little q over the radius of the big sphere, big R, is equal to V2. 1 over 4 pi epsilon naught little q over R. And so you can see that the 1 over 4 pi epsilon naughts disappear. I have big Q minus little q over big R is equal to little q over R. I'll leave you to do the rest of the algebra, but what I get is little q equals big Q divided by big R over little r plus 1. So when you do that bit of arithmetic, you can see that I can find the amount of charge that is transferred because the amount of charge that is transferred is little q. And I can solve for this because I have big Q. Well, I have an expression for big Q. I have big R, 13 centimeters, and little r, which is 5.2 centimeters, and I can actually solve for this value. So I'm going to write big Q as this expression 4 pi epsilon naught VR. And so I'm going to write it as 4 pi epsilon naught is 8.85 times 10 to the minus 12 times V, which is 4,500. They told us it's 4.5 kilovolts, the initial potential on the big sphere. And the value for the radius of the big sphere is 0.13 in meters. And all of this divided by big R over little r, I can leave it in centimeters, 13 over 5.2 plus 1. And if I do this calculation to two significant figures, what I find is the charge that's transferred is 1.9 times 10 to the minus 8. So 1.8 times 10 to the 1.9 times 10 to the minus 8 coulombs is transferred to the small sphere. If I wanted to, I could find what is remaining on the large sphere, but it wasn't asked of me. So there were quicker ways. You could do this just by using your insight and doing the mathematics immediately. But I find that this is a more complete start to finish method of this kind of problem. So try doing the problem in the most basic way possible, starting from the ground and going to the answer, and then try to get more efficient. This is a very long method. But if you understand the picture, you can obviously do this much quicker. And 3 marks may very well take you 4 minutes, maybe a little bit more, but nothing that will set you back in your overall exam. So a 7-mark question, but this last sub-question could have made it a fairly long question altogether. Interesting one, very nice question that will challenge your problem-solving techniques. The next question is number 201, and this is from the March 2020 exam. It's question paper 4, variant 2, and question number 6 from that paper. We're told that two positively charged identical metal spheres A and B have their centers separated by a distance of 24 centimeters. The variation with distance from the center of A of the electric field strength E due to the two spheres along their line joining their centers is represented by the figure. Aha, so we're back to electric field strength first distance, but now for two spheres rather than one. And we are asked to calculate the radius of the two, or state rather, the radius of the two spheres. So they expect me to look at this graph and just be able to read the radius off. Well, I know that they're identical, so they both have the same radius. They both look exactly the same. They may not store the same charge, but they look exactly the same. And what I can see is that the electric field strength is 0 between 0 and 2 centimeters and 0 between 24 and 22 centimeters. So the first 2 centimeters to the right and to the left have electric field strength of 0. And that's the distance measuring from the center of each sphere to the surface. that distance is the radius. Remember, electric field strength is 0 inside a conductor. And so I can read the radius as 2 centimeters because I know the electric field strength is 0, I'm inside the conductor. If I go from center to surface, that's the radius. So the radius for both is 2 centimeters. As you can see, x is measured in centimeters. We're then told that the charge on sphere A is 3.6 times 10 to the minus 9 coulombs, and we want to determine the charge QB on sphere B. We want to assume that A and B can be treated as point charges at their centers. So I need to figure out what the charge on Q on B is, but I'm also not given any explicit information besides the graph. I have to take information from the graph. So what I'm going to do is I need to write an equation. Obviously, I have to make something equal to something. But on the graph, I can only see one point where two things are actually equal. It's the point where the net electric field strength is 0. Electric field is a vector. So the net electric field is electric field due to A plus the electric field due to B. So I can see that at 16 centimeters, they both have the same strength in opposite directions. And so the net electric field strength is 0. This means, and they asked me to explain my working as well, so I'm going to do just that. At x equals 16 centimeters, the electric field strength of A equals the electric field strength of B, because I can see the net field is 0. So what I can tell from this is if I write the equation down, the mathematical expression for the electric field strength at A, it's 1 over 4 pi epsilon naught QA over RA squared, that's the charge on A divided by the distance to that point, is equal to 1 over 4 pi epsilon naught QB over RB squared. So what this means is the charge on sphere B, QB, as you can see the constants disappear, is equal to the charge on A times the ratio of distances to the neutral point, RB over RA all squared. And all of these are known. So the charge on A is 3.6 times 10 to the minus 9 coulombs, which I've been given. The distance to the neutral point is 8 centimeters from B and 16 centimeters from A, all squared. And what I get is 9 times 10 to the minus 10 coulombs. So the charge on sphere B is 9 times 10 to the minus, not 9, but minus 10 coulombs, or 90 nanocoulombs. And so you can see that when you're given a graph and you want to find something special about the second sphere, if you know some information about the first, a good idea would be to say, look at the point at which the electric field strength is 0. That means the individual electric field strengths must add, or in this case subtract, to give you 0. And so we can equate the two magnitudes of electric field strengths and solve for the thing that's unknown. In this case, it was the charge. We are then told that sphere B is removed and we want to use the information from B to determine the electric potential on the surface of sphere A. Well, right now this is not going to trouble us at all. Potential is 1 over 4 pi epsilon naught QA over RA. Q over R for potential. 1 over 4 pi epsilon naught, I know I can write this as 8.99 times 10 to the power 9 meters per farad. That's 1 over 4 pi epsilon naught. The charge on A we were given as 3.6 times 10 to the minus 9 coulombs divided by the radius of A, distance from the center to its surface, 0.02 meters, 2 centimeters. And what I get the potential to be on the surface is 1.62 times 10 to the power 3 volts, or 1,600 volts, two significant figures. Or I could say 1.6 times 10 to the 3 volts. So you can see that every subsequent question now becomes easier because of the difficult work we had to do in the first part. We're then told to calculate the capacitance of sphere A. Again, this is not going to cause us too much trouble. Capacitance is defined as charge per unit potential. At the surface, the charge is 3.6 times 10 to the minus 9 coulombs. The potential is 1,600 volts. And so what we get is a very low potential, 2.25 times 10 to the minus 12 farads. And to two significant figures, this is 2.3 times 10 to the minus 12 farads, or 2.3 picofarads. So that question was also interesting because we have to be able to combine electric fields with capacitance. It's very rare that capacitance electric fields will be separated. As many topics in A-level physics, we need to be able to combine concepts and ideas when solving these paper 4 questions especially. The next question is number 202. This is the last question for this video, and this comes from the summer exam of 2019. Question paper 4, variant 1. And this is question 6 from that exam paper. We are told firstly to state two different functions of capacitors in electric circuits. Now there are many functions of capacitors. You can talk about tuning, you can talk about changing resistance, or rather changing frequencies in radios, but that's all part of tuning anyway. But what we've learned is one that we can use capacitors to improve smoothing. Or if you don't want to say improve smoothing, you could say something more quantitative, to reduce ripple, because ripple is a measurable value. Reduce ripple on rectifiers or in rectifiers. And so we've seen the applications of this firsthand. We've seen how capacitors can be used to smooth or to reduce the ripple in rectifiers. And another function of the capacitor will be to store electrical energy, as we do in a battery. So I store electrical energy. Yes, the electrical energy will be released much quicker than it would with a battery, but it still stores the energy. Still can be used for a purpose that a battery could, maybe in some cases, be used for. So very simply, to improve smoothing or reduce ripple in rectifiers and to store electrical energy. Simple, short, but correct. We're then told that three uncharged capacitors of capacitances C1, C2, and C3 are connected in series with a battery of electromotive force E and a switch as shown in the figure. When the switch is closed, there is a charge plus Q on plate P of the capacitor of capacitance C1. Show that the combined capacitance of three capacitors is given by 1 over C is equal to 1 over C1 plus 1 over C2 plus 1 over C3. Essentially, they're asking us to derive the equation for equivalent capacitance for capacitors in series. Now, what I know is that if there's a charge Q on C1, then C2 has a charge Q, and C3 has a charge Q. The charge must be same everywhere in the series circuit. Charge has nowhere to split, so it must be the same. Plus Q is induced on the left-hand plate of C1, and so minus Q is induced on the right-hand plate, which goes to C2, and the whole process continues. So what I know is that the EMF, since these are three components in series, they are potential dividers. So the total EMF is equal to the potential difference across C1, the first capacitor, plus the potential difference across the second capacitor, plus the potential difference across the third capacitor. Like resistors in series are potential dividers, so too are capacitors potential dividers if they are in series. But the total EMF is equal to the total charge in the circuit Q divided by the total capacitance, the combined capacitance C of the three capacitors. But the potential difference across 1 is the charge on 1, which is also Q, divided by its capacitance C1. The same for V2. Total charge is also Q, divided by its capacitance C2. and V3 is total charge Q divided by its capacitance C3. Since charge Q is constant, we can see that if I divide through by Q, which I can do, I get 1 over C is 1 over C1 plus 1 over C2 plus 1 over C3. And this is what we were asked to show. So remember, when we have capacitors in series, whatever charge one capacitor gets, all the capacitors get. Charge is not splitting, it's not branching off anywhere, so it has to be the same charge through each capacitor. And so that's the basic idea we can use to derive that expression. And you may have done this whilst you were studying the concepts of the topic. We're then told that a student has available 4 capacitors, each of capacitance 20 microfarads. We want to draw circuit diagrams, one in each case, to show how the student may connect some or all of the capacitors to produce a combined capacitance of firstly 60 microfarads and then 15 microfarads. So, to be honest, this question can be a little bit of trial and error, but the first thing I usually do when I get a question like this is to try and put the 3 capacitors in series first, and then put them in parallel and see if I get any of these values, 60 or 15. To my luck, it does work in this problem. And if I take these 3 capacitors, each have capacitance 20 microfarads, and I connect them in parallel, 20 plus 20 plus 20 gives me 60. So what this means is I have 1 capacitor, 2 capacitors, 3 capacitors. I don't really have to label this diagram because all of the capacitors are identical. They have the same capacitance. And I just need to draw all 3 of these capacitors in parallel. And I have current going in there, splitting, rejoining, and so this is clearly a parallel branch, and I don't have to label anything, but this is C1, C2, and C3. So the total capacitance for capacitors in series is parallel rather, C1 plus C2 plus C3, which in this case is 60 microfarads, 20 plus 20 plus 20. They didn't ask us to do the calculation, they only asked us to draw the diagram. So the diagram was more than sufficient. How do I now get and look, I don't have to use all 4 capacitors. So they did ask us to show how the student may connect some or all of the capacitors. It would be a lot more difficult if they asked us to use all 4. But they did say some or all of the capacitors. Next, we need to put the 4 capacitors together to try and get a capacitance of 15 microfarads. So again, this is a little bit of trial and error. And you'll find that what works is taking 3 capacitors, putting them in parallel, and getting an equivalent capacitance of 60 microfarads like we did before. But then in parallel, or rather in series with this parallel connection, I have the last capacitor. So the equivalent, or 1 over the total capacitance, is 1 over 60, which is the equivalent capacitance of the branch, plus 1 over 20. And what this means is that the equivalent capacitance is 15 microfarads as required. So like I say, this does require a little bit of trial and error, and you'll find patterns that will make this easier when the question is like this, but randomized with the values. And it just becomes a bit of mathematical manipulation at some point. And again, you're only asked to draw the diagram, not to do the calculations. I always prefer doing the calculations aside to make sure that I haven't made an error in my head if I'm doing the mathematics in my head. And that was another 7-mark question. And for this video, that was the last question. But in a later video, I will tackle the problems on capacitance at the end of the sheet of problems, which will look at the structure of capacitors themselves and look at the energy stored in capacitors and so on. And so I hope this was useful. I will be making more videos on the remaining topics for paper 4 and answering some more topical past paper questions. So let me know if this video was helpful. Leave a like, leave a comment, subscribe to the channel if you haven't already. And I'll see you again next time on Everything is Relative. That's all from me for now, Mr. K. I'll see you again next time.